Welcome back to the course Fluid Mechanics. Let us discuss the last segment of fundamental properties of fluids. The next property is surface tension with the symbol sigma. As defined, this is a property of a liquid surface displayed by its acting like a stretched elastic membrane. For gases, this is the property behind bubbles and the definite droplets with fluids. This is also the main reason why insects are able to step on a fluid surface or when coins or things are able to float on fluids. Checking on the formula, we do have sigma is equal to F all over D, where sigma is denoted as surface tension, F is equal to the force, and D would be the length along which the force is felt. The English unit for our surface tension is given as dyne per centimeter, while the SI unit would be taken as Newton per meter. Let us check on the first example for surface tension. A toothpick 5 centimeters long rests on the surface of the water without getting wet. What is its weight if the surface tension of water is 0.07 Newton per meter? Let's take note that water wets the toothpick from its two sides. Thus, the formula of sigma is equal to F all over D would turn out as F all over to twice the length. Now, if we are going to plug in our values, 0.07 Newton per meter is equal to the weight all over twice of 0.05 meters, which would give us weight is equal to 0.07 newtons. Let us check our next example. A plastic ring of 3 cm radius is rested flat on the liquid surface. When slowly raised, it is found that the pull required is 0.04 newtons more before the film breaks than after. Find the surface tension of the liquid. Similarly, the water wets both the inner and outer sides of the ring. So, our formula sigma, which is equal to F all over D, would turn out to be F all over twice of the circumference. If we are going to plug in our values, sigma is equal to 0.04 newtons all over twice the circumference with the formula 2 pi r, which would be equal to 2 times 2 pi times 0.003. After computing, sigma would be equal to 1.06 Newton per meter. Let's check on our third example. A coin of 0.01 meter radius is rested on the water surface. Calculate the force required to take it away if the surface tension of water is 0.075 Newton per meter. Unlike what we have with the previous example, we do have a circular plate this time, where water wets only the outer edges of a circular plate. So, our formula of sigma, which is equal to F all over D, would just turn out as F all over circumference. So, plugging our values, 0.075 Newton per meter would be equal to F all over 2 pi r, where r would be taken as 0.01 meter. Thus, our value would turn out as F is equal to 0.0047 newtons. The last fluid property is known as the capillary action. This is the property which enables fluids to ascend through some medium due to some forces. You might remember way back in your elementary years when your science teacher asked you to bring some plants, dye, and water. Placing the plants into the water with some color, this color would have risen up to the plant's leaves. Similarly, when you are going to place a block of foam with some colored liquid, this liquid would also ascend. Just the same, using a tissue paper with some colored fluid, the fluid would be rising up to the tissue paper or our medium. This illustration is from Dr. Keith Hayward showing capillary action of water. Without capillary action, the water level in all tubes would have been the same level. Smaller diameter tubes have more relative surface area inside the tube, allowing capillary action to pull water up higher than in the large diameter tubes. There are three main variables that determine whether a liquid possesses capillary action. The first one is what we call cohesive force. This is the intermolecular bonding of a substance where its mutual attractiveness forces them to maintain a certain shape of a liquid. The second is surface tension. This occurs as a result of like molecules and cohesive forces bonding together to form a somewhat impenetrable surface on the body of water. And thirdly, we do have adhesive force. When forces of attraction between unlike molecules occur, it is called adhesive forces. In our illustration, capillary attraction would happen if adhesive force is greater than cohesive force. Likewise, capillary repulsion happens when cohesive force is more than adhesive force. The formula for our capillary action properties given as H is equal to 2 sigma cosine theta all over rho GR. Another would be from Jurin's law stating that H times R should be constant. Sigma is given as the surface tension. Theta would be the angle of contact. Rho is mass density of the liquid. G would be the gravitational acceleration. And R would be the radius of the tube in the liquid. Let's check on our first example. Water rises to a height of 4.5 centimeters in a capillary tube of radius R. Find R assuming the surface tension of water is 72 dynes per centimeter. Take the angle of contact of water in the glass as 15 degrees. Density of water is still 1,000 kg per cubic meter. Before we are going to plug in our values to the formulas, take note that 72 dynes per centimeter can be converted to 0.0072 Newton per meter. Having our formula, H is equal to 2 sigma cosine theta all over rho GR, we can extract R as 2 sigma cosine theta all over rho GH. Plugging in our values, R is equal to 2 times 0.0072 Newton per meter cosine 15 degrees all over 1,000 kg per cubic meter times 9.81 meter per square second times 0.045 meter, giving us the value of R as 0.315 millimeters. Checking on our second IP, a liquid rises to a height of 9 centimeters in a glass capillary of radius 0.02 centimeters. What will be the height of the liquid column in a similar glass capillary of radius 0.03 centimeters? For our comparison of glass tubes, it would be best if we are going to use Jurin's law. We said that Jurin's law states H times R is equal to constant, wherein H1 times R1 should be equal to H2 times R2. If we are going to denote H2 as our required height of the liquid column, H1 times R1 all over R2 would be the following formula. So plugging in our values, 9 centimeters times 0.02 centimeters all over 0.03 centimeters would give us H2, or the height of that liquid column, as 6 centimeters. Hang on tight. Moving on to principles of hydrostatic pressure.